All right, this is part 2 of 7.01 hydrocarbons. So ethane, ethene, and ethine all have 2 carbons. Ethine has the highest melting point. Why? It has a triple bond. And triple bonds take a lot more energy to break versus a double bond. And double bonds take more energy to break than a single bond. So then I just drew them out for you so you can see them all there. So even though they all have 2 carbons, they have different properties because, again, of having a single, double, or triple bond. Cyclic hydrocarbons have geometric structures. Because carbon can bind to other carbon atoms, the ends of a chain can bond to form a ring structure called a cyclic hydrocarbon. The rings can form geometric shapes that depend on the number of carbons involved. For example, cyclopropane has 3 carbons and forms a triangle. Cyclobutane has 4 carbons and forms a square. The name implies the number of carbons, and the cyclo prefix means the structure is a ring. The rings in cyclic hydrocarbons are composed of single carbon-carbon bonds. For cyclic hydrocarbons with more than 5 carbon atoms, the ring structures are not flat. What is the difference between octane and cyclooctane? Both compounds have 8 carbons, but cyclooctane or cyclooctane is a ring structure versus if you just have octane, it's just 8 carbons in a row. So this is a model of cyclohexane, so hex like hexagon. Each vertex represents a CH2 group unless otherwise indicated. So whenever you have a corner, you know you have a carbon. Carbons go in the corner. They can draw it like this, so now you can see the carbons are still at the corners, but you have hydrogens on them. So here's my carbon, and it needs to make 1, 2, 3, 4 bonds, or we can draw it as molecules. Although this ball and stick model is a more accurate representation of what a real molecule looks like, it is still simply a model. So again, each carbon has 1, 2, 3, 4 bonds to it. Under cyclic hydrocarbons, I added an example. Octane is a chain of 8 carbons with hydrogens, and cyclooctane is a ring of 8 carbons with hydrogens. Note a corner on a ring represents a carbon atom. Molecules may be represented by ball and stick model. Because of the 3-dimensional structure of organic compounds, and because many organic compounds have the same formula, drawing the organic compound is important. One method uses element symbols connected by straight lines for single bonds, double lines for double bonds, and triple lines for triple bonds. The position above and below the plane of the molecule is important. Ball and stick or space-filled models are also useful. So in other words, this is 3-dimensional. Okay? And different models give different perspectives and information regarding the composition and structure of organic compounds. And that is a good summary sentence for that. So sometimes we draw it with lines. Other times you will build it with, they call it ball and stick models. So both are helpful. Aromatic hydrocarbons have flat ring structures. Another class of ringed hydrocarbons is called aromatic hydrocarbons. Benzene, a solvent, is an example of an aromatic hydrocarbon. So solvent means it can do what? It can dissolve a solute. So benzene has 6 carbons and the electrons are shared along the whole ring. This sharing is often represented by showing bonds between the carbons as alternating single and double bonds. Other times, this sharing of electrons among the carbons of the ring is shown as a circle in the middle of the ring. This bond combination also gives the ring a flat structure. Aromatic hydrocarbons may be composed of more than one ring structure. Okay, this is the skeleton model of benzene. So each corner is a carbon. So 1, 2, 3, 4, 5, 6 carbons, 6 corners. These 2 share a double bond. These 2 share a single bond. These 2 share a double bond. These 2 share a single bond. You can also draw it like this. So this circle represents the fact that you have double bonds happening. This is a more compact representation of a benzene molecule. The ring indicates the sharing of electrons among the carbon atoms. And of course, the ball and stick, where you can see some of the hydrogens as well. And actually, I should have said all the hydrogens. You can see all the hydrogens as well. And I just added to our definition that it's shown by alternating single and double bonds or by a circle drawn inside the ring. Many organic compounds have functional groups attached. Okay, so I want to show you a model. So in our model, we are going to use the ball and stick figure, and we have carbon. And carbon has 4 open holes in it, and those open holes represent what? They represent the bonds that can be made. So when you use these, the sticks are representing where the electrons go. So there's 4 places, and we can put a hydrogen on. And if you put the hydrogen on, hydrogen is in group 1. It has 1 valence electron. Well, it only has a total of 1 electron. So therefore, it's only going to make a total of 1 bond. Okay. Now, the carbon, of course, can attach itself to other carbons. And if need be, it can make a double bond. And so when it makes a double bond, you're going to have 2 of the electrons being shared between 2 of the molecules, and it's going to look like this. Now you can see I have a very simple cyclic hydrocarbon, and would this one be considered aromatic? And, and yes, it would. Why? Because you have alternating double and single bonds. So because they're alternating double and single bonds, it would be considered aromatic. And as you can see, it is flat. So I could lay it flat on the counter or flat in my hand. All right, so I made another cyclic, and this one is not aromatic. Why not? It has all single bonds in between the carbons. And you'll notice, hopefully, that I can bend this a little bit. So there's actually a little bit of wiggle room, and sometimes you do have the nice flat molecules, but you notice here I also have some dimension going on in this direction. So that's why when they talk about chemistry, they talk about building them, because you can really see more to it. Here's another example. I could have this be a chain. Well, in some cases, maybe one of the carbons is upright. Okay, maybe 2 of them are upright. Okay, so these different angles actually cause different properties, and that's part of what makes organic chemistry so unique. All right, now let's talk about these functional groups. Many organic compounds have functional groups attached. Carbon can also form bonds with other atoms besides carbon or hydrogen. Many of these atoms are part of a special arrangement of atoms called functional groups. Functional groups can be specific organic groups, such as CH3, which is methyl, or other atoms, for example, an alkyl halide, such as chlorine. The chemical reactions in which organic compounds participate are often determined by the specific functional groups present on the molecules involved. For instance, in alkyl halide functional group on one organic molecule can replace a hydrogen atom on another organic molecule. Organic compounds can be classified according to their functional groups. One such class is the alcohols. And the alcohol is any hydrocarbon with at least one hydroxyl or OH group. So here they have some of the common functional groups. Okay, so you start out with your basic alkane or alkene or alkyne. Okay, then in these empty spaces at the end, you pop off a hydrogen and you can add something like an ether, an ester, an alkyl halide, an amine, an alcohol. It can be phenol. You can add an amide, an aldehyde, a ketone, or a carboxylic acid. Okay, so basically what they're showing by that, I'm going to demonstrate on the molecule. All right, can you name this? This is propane. I know it's propane because there are 3 carbons, and each of the carbons has a single bond, and I'm missing a hydrogen at the end. There you go. So this is propane. Now, what they're saying is I could add a functional group. I could pop off one of these hydrogens, and instead I could, let's say, replace it with chlorine. Okay? So the chlorine would be my functional group. It's the thing that you pop off a hydrogen for, oops, and then you add something very specific to it. So another one that they gave you as an example was for alcohol. So alcohol is going to have an OH group on it. And notice it's not OH negative, because what is OH negative? OH negative from your acids and bases, hopefully you remember, is hydroxide. So I can take an alcohol, which would just be an oxygen with a hydrogen on it, and I popped a hydrogen off here, and so I could just put this functional group or that alcohol on the end to get a totally different compound. So that's what they're showing you on the screen with the functional groups. So I added to our note various functional groups, remove a hydrogen and replace it with one of these groups for new properties and a new compound. And then I just copy pasted them down there. Alcohols have a hydroxyl functional group. The functional group that defines alcohols is the hydroxyl group, OH. One or more OH groups can be attached almost anywhere on a carbon chain or ring. Many alcohols have a single OH group located at one end. The hydroxyl group allows alcohols to have strong hydrogen bonds, which affect their solubility, boiling points, and freezing points. You may be familiar with several types of alcohol. Isopropyl alcohol, or rubbing alcohol, is used as a disinfectant. Methanol, or wood alcohol, is used as a fuel. Polyethylene glycol is a major constituent of antifreeze. Ethanol is the type of alcohol found in wine and beer. It is also added to mouthwashes and cleansers to kill bacteria. Phenol has a hydroxyl group connected to a benzene ring and is another disinfectant. All right, so we'll look at our alcohol groups here. And you see we have methanol. So we would have methane, but we added the OH, so now instead of methane, it's methanol. Instead of ethane, which would just be the CH2CH3, now we have ethanol because we added the OH. 1-propanol. 1-propanol means the first carbon has the OH. If we put the OH here, then it would be 2-propanol. Okay? 1-octanol, so 8, like octopus. Octanol, we have 8 carbons. On the first carbon, we have an OH group. Isobutanol. Okay, so the reason it's iso has to do with the fact that it's branched. We have 2-methyl-1-butanol. Okay, so that means on the first carbon, we have the alcohol. On the second carbon, we have a methyl group. Isoamyl alcohol. So again, we have the alcohol on there, and we have that chain. And then benzyl alcohol, we have our ring. And then, of course, we have the alcohol on the end there. And note, you're not expected to memorize all this. And so I added that alcohols have at least one hydroxyl group, can be attached almost anywhere on the carbon chain or ring, usually at one end. The OH group allows alcohols to have strong hydrogen bonds, which affect their solubility, boiling points, and freezing points. The system for naming organic compounds is based on the compound's features, which I've been alluding to this whole time. The International Union of Pure and Applied Chemistry has a system for naming organic compounds. The names are specific and will detail where important features, such as multiple bonds, functional groups, are located. Naming conventions include the following. Number of carbons is a specific prefix. Type of bond endings, single ane, double ene, triple ine. Cyclic hydrocarbons, the prefix cyclo before the name. Location of multiple bonds. For ease of communications, chemists often number the carbon atoms. The bonded carbons are numbered before the name. For example, 1,2-butane versus 2,3-butane. Location of functional groups, carbon number of the group before the name. For example, 1, chloropropane, 2, chloropropane. So on this one, the chlorine is on the first carbon. On this one, the chlorine is on the second carbon. And of course, going through how many carbon atoms go with what prefix. So meth is 1, eth is 2, prop is 3, but is 4, etc. etc. And we'll continue in the next